let me recall what we are doing at this point. First, we define the data structure heap. Basically, it is an array. The underlying data storage object is just a simple array, but we do some special treatment. What we did there, just define special relationship between parent-child nodes. Yeah. Use inequality. All right. Yeah. After that special condition, well, then we have a binary tree stored in an array. That binary tree is a special type. We call it a near complete binary tree. Yeah, not a complete, a near complete. Yeah, only the bottom level may not be full. Other than the bottom level, all the other levels are full. Yeah. All right. And we also, find a procedure to build that heap. Yeah. So last time we used example to show how to build a heap. Yeah. Today, we will do analysis. How much is the cost? Yeah. Last time I wrote big O of n as the cost, but how do you see that, right? Why you say big O of n is the building cost? Yeah. So today we will find the answer, yeah. But we need to do a lot of work to find that answer. So let's start the title. Yeah. B.2, building cost of a heap. Yeah. All right. To do the building cost, first, let us answer a simpler question first. Yeah. The simpler question, but we need to do one by one. Yeah. Combine the cost of all heights. First, we have this concept called heights. Yeah. Because we have a binary tree, then there is a height concept. Yeah. Here, let me just draw a simple diagram. For example, this is a binary tree. All right. All right. Okay, yep. But this is a general binary tree, all right? Yep. It's not a heap. Yeah, the reason is it's not a near complete binary tree. Yeah. Here I'm talking about height concept for a general binary tree. Yeah. So what is the height? When we define the height concept, we talk about for each node has its own height. Yeah. What is the height number? We define the bottom level as the ground level, right? The bottom level, yeah, the bottom level, yeah, here, the bottom level, all right? Ground level means the height is 0. Yeah. All the nodes on the ground level with height 0. Then for this height 1, because when we start from this node and we move toward the bottom, the number of edges is 1. We count the number of edges from the current node to the bottom level, the number of edges we need, that's the height number. All right. Similarly, for the height of this node, 2 edges. So the height equals 2. The root node, yeah, for the root node, then the situation is a little more complicated, because if we start from the root node, then from there to the bottom, you may have 2 different paths, right? One path like that, 2 edges. Another path to this bottom, 3 edges. Which one you use as the high number? Longest. Yeah. Yeah. If it's not longest, because we cannot use it to define the high concept. Yeah. The longest, that is 3. Yeah. You can see, yeah, based on our natural understanding, it should be the longest, right? Yeah. Yeah. So here we use the longest path to define the height concept. Now, with this concept, we will study the cost of all heights. What do you mean the cost of all heights? Yeah. Because after we define the heights, we may have 0, 1, 2, 3, 1 by 1, and so on. The highest, the top, at the root, log base 2 of n. That's the high number. For 0, no cut. 0, we do nothing, right? Ground level. We do nothing. So then we start from height 1, height 2, and so on until the top one. Yeah. We look at the, max heapify cost. Yeah. When you do max heapify operation, there is a cost. Yeah. So we will calculate that cost. Max heapify is used in our building a heap procedure. Building a heap procedure, we use max heapify operation. Yeah. So that's, yeah, with that background, we can consider the total cost. All right, so let's start, yeah, with high number start. But when we start, we start from the ground level, 0 height. All right. The cost of max heapify for all nodes of height h. Yeah. So this h from 0 through log of n. Okay, yeah. And here, oh, just a minute. Yeah, I skipped something. All right. Yeah, it's not good. Yeah. All right. Yeah, because this part, yeah. Remember, this part is B.2. Yeah. I skipped that B.1. We need to start from B.1. Yeah. Here, because look at that. Yeah. Before I go back to B.1, the heapify cost is this much. The question is, how do we know this much, right? We need to find it. That is our work in B.1. Okay, that's the B.1. We find it. Okay. Now let us go back to B.1. We find it. Then we continue from this point. B.2, we'll continue from this point. Yeah. All right. Yeah. I noticed the problem. B.1. Yeah. B.1, all right, here. Oh, not there. Yeah, because I need to moving up. Yeah, B.1 is here. Heap nodes in each level. Yeah. We need to calculate number of heap nodes in each level. All right. Then we can look at the building cost. All right. Yeah. For this part, first, let us look at a relatively simple question, but non-trivial. So we need to do some interesting work here. Number of leaves in a heap. You know the definition of leaves, right? Yeah. Definition of leaves. Nodes without child node. All right. So nodes, leaves or leaf nodes. So nodes without child nodes. That's the definition of leaves. All right. The question is, given a heap, how do we calculate the number of leaves in a given heap? That's the first question. All right. Yeah. To answer that question, we need to describe the leaves. We need to use formula to describe the range for the leaves, the range for the indices of the leaves. We need to do this work first. Yeah. First, from this diagram, let us look at what are the leaves in this diagram. Yeah. We know nodes without children. All right. Yeah. Nodes without children. Yeah. And from the figure, these 5 nodes do not have children. Yeah. So the number should be 5. Yeah. So let us look at total number of nodes. Total number n equals 10, right? Yeah. The number of leaves equals 5. Look at this. What is the relationship? All right. So let us find that formula first. In order to find formula, we need to study parent-child relationship. Okay. Parent-child relationship. If we know the position of the parent is I, A of I is our parent node. Then the child node, we use A of 2I, and here we use the left child node. Left child node. Why not right child node? Why we use left child node here, not right child node? Because the right child node may not be available. We may have the situation, this parent node has a left child node, but no right child node. That's possible, right? Think about that. Yeah. A node that could have a left child node, but no right child node. So it's better we use the left child node, not right child node. Yeah. All right. So here, I and the 2I, that kind of relationship. All right. Yeah. From this 2I, yeah, let's think about what the condition we need when we know the left child node has the position 2I. When we describe a leaf, so here when we talk about leaf node, we mean this one is a leaf node. How about that? The parent. Think about if the parent corresponds a leaf, what this 2I should be. Parent with position I corresponds a leaf. How can we say about its left child position 2I? Out of range, right? 2I cannot be within the range, right? Within the range of positions for all the nodes in this heap, right? If 2i is within the range, then its parent cannot be a leaf. Think about this statement. If the index of the left child is within the range we mean between 1 and n, that range, okay, in that range. Oh, it looks like the response a little slow. I wrote for a long time, yeah. After many seconds, then it is displayed, yeah. All right. Next, out of bound. When you describe this out of bound condition, what do we mean out of bound? 2i out of bound. Okay? When 2i greater than n, it is out of bound, right? If 2i less than or equal to n, that's not out of bound. So let us write that. Meaning of no child. What's the meaning of no child? That's the leaf definition, right? Meaning of no child. Okay. Yeah. All right. Condition. When n is greater or equal to I and less than 2i. Yeah. Now you know, because 2i is greater than n, it is out of bound, right? When 2i out of bound, that means the node with index I cannot have any child. How about that statement? The node with index I cannot have any child. So this condition corresponds to this description, meaning of no child description. So we have this inequality. Let us simplify this inequality a little bit. Yeah. So our index range, yeah, that's the valid index range for the heap nodes. Yeah. Do division by 2, we have n over 2 less than I. But this I must be an integer, right? The index I must be an integer. n over 2 may not be an integer, right? N over 2. Sometimes integers, sometimes may not be integer, even odd, right? Yeah. But we want to have integer expression for I as the lower bound from this inequality, the lower bound. So what is the expression for the smallest such I? Integer expression, smallest such I. Yeah. Here, let me write this expression using the ceiling function. Floor function. Yeah. Floor function of n over 2 plus 1. Yeah. That's the smallest I. Think about that. Yeah. When n is an even number, n over 2, that's an integer, but I should be greater than that integer. So n over 2 plus 1. When n is an odd number, n over 2 is not an integer. So the floor function, we rounded it down, and then we need to plus 1 to raise it higher than n over 2. So you can see this expression is good one. Yeah. All right. Smallest such I. That is the integer expression. Yeah. All right. So now we can write range for leaf nodes. So now we're ready to write the range for the leaf node. That's the here. This is the range. We give lower bound, upper bound. This is the lower bound. And upper bound n. Upper bound is simple, right? The largest position number n. Upper bound simple. Lower bound, we just find it. Yeah. All right. with this range, can you tell me how many nodes are there in this range? How many nodes are there in this range? We need to do counting. How many eyes fall in this range? You do subtraction. The answer is use the upper bound and minus one smaller than the lower bound. Do not just the upper bound minus the lower bound. You need to plus one back. Upper bound minus lower bound, then plus one back. So you get that n minus floor function of n over 2. That is the final number expression for the number of leaves in a given heap with n nodes. Then you can check our example here, n equals 10, 10 minus 5, number of leaves, 5. All right, okay. Then the next step, we can simplify this n minus floor function of n over 2 to one-term expression, from two-term expression to one-term expression. A little simpler, but this one-term expression, we use the ceiling function. Ceiling function, not floor function, ceiling function. Why it is correct? You may wonder why it is correct. Here I refer to our textbook, page 477. This formula is given there. Okay. If you want to prove it, then you can prove it. To prove it, that's pretty simple. Consider when n is an even number, it's easy to see both sides are equal. Then you consider when n is an odd number, then you do some simple calculation. You can also see both sides are equal. So it can be proved easily. Here, let us just use this formula. So we get this a little simpler formula. Later we will use it. When we move to B.2, we will use this formula. All right. Now let us move to the next round. We just complete one formula development with our h equals 0, right? That case, that special case. Now we need to move to h equals 1 case, and so on. Later we can find some special rule, so we will get a general formula later. Now the question. All right. Number of internal nodes with height 1. So here, I use this special term, internal nodes. You may want to ask, what's the meaning of internal nodes, right? The nodes that is not leaf, non-leaf, internal. So here, internal nodes and external nodes. External nodes means a leaf node, okay? Means non-leaf node. That's simple, okay? So the number of non-leaf nodes with height 1. Actually, if it's height 1, that cannot be leaf, right? All the leaf nodes have height 0. So if it has one node has height 1, it cannot be a leaf node, right? Let's look at a binary tree, a heap. This one is a near complete binary tree. So we can imagine it is a binary tree for a heap. Can you tell me what are nodes with height 1? At the beginning, I explained the height meaning, right? The concept height, definition, concept height at the beginning. Yeah. You know, I did it in part B.2, you know, it's a wrong starting point, but we can use our understanding from there. Yeah. Height 1 nodes. Let us find those height 1, mark those height 1 nodes. These two has height 1, right? And another one also has height 1. So from this example, we have 3 nodes with height 1. Yeah. But we need to develop a formula. Okay. So let us continue our similar development from the previous slide. Yeah. The consideration, very close. Yeah. The number of our goal, we want to look at it. Yeah, so here, yeah. All right, before we do that one, first let's answer this question. Because it's simple, number of all internal nodes. How do we write expression for the number of all internal nodes, non-leaf nodes, excluding the leaf nodes, the remaining, that's the number of internal nodes, right? Yeah. Total nodes n. N equals the number of leaf nodes plus the number of internal nodes, right? But we know the number of leaves, this number. Although we can use the simpler expression, seeding function of n over 2, yeah, but that's not important, okay? Yeah. We can use either one. All right. Now the number of internal nodes. Pretty obvious. Floor function of n over 2. Yeah. Because these two lower expressions adding up should be the same as the total number n. Yeah. So that's the number of internal nodes. Okay, all right. Now, next question, we want to find the number of internal nodes with height 1. That expression should be smaller than the number of total internal nodes, right? Should be smaller than that. Yeah. Let us count the number of internal nodes with height 1. Yeah. To do that, then we need to use a key property to describe these nodes, these internal nodes with height 1. How do we describe it? Here, I use this sentence. Their children are leaves, right? First, they have children. They must have children first because they are internal nodes. All internal nodes must have at least one child, right? Yeah, they must have children. But in order to describe height 1, we know their children must be leaves. Must be leaves. That address the condition. Their height must be 1. Okay, yeah. Now we can look at the children. Their children, the children location 2i, left child location 2i. 2i must fall into the leaf range. What is the leaf range? This is the leaf range we developed from the previous slide. So this is the leaf range, lower bound, upper bound, but for the height 1 internal node, we use 2i in between, 2i expression in between. Now let us simplify this inequality. After division by 2, we have this expression. You may feel, jumping too fast, right? Jumping too fast. Yeah. The right-hand side, you can see a little easier, right? Right-hand side, division by 2, but you need to take the floor function because I must be an integer. So you feel it's okay by taking the floor function. But how do you see left-hand side? Division by 2, then taking ceiling function, why you have the lower bound for I? Yeah. Here, I jump a little fast. Actually, I need to show you another intermediate step. Then you can get here with better understanding. So let me show you the intermediate step, this one. Yeah. In this inequality, sorry, not inequality, equality. In this equality, the left-hand side, that should be the one, that should be the expression we use from the first inequality to division by 2. Okay, yeah. But I do simplification. This is the simplification I did. Okay, yeah. Simplification. You may ask me, how do you do the simplification like this? Yeah. When you do simplification, you need to consider the cases for n. Division by 4 with remainder 0, 4k. 4k plus 1, 4k plus 2, and 4k plus 3. With remainder 0, 1, 2, 3. You try these 4 cases to verify both sides of the formula. A little more work. You need to verify 4 cases. Then you can prove this identity. This identity. All right. Yeah, here I skip that verification step. If you want to do the verification by yourself, you can do it on the scratch paper. Yeah, it's pretty easy. Yeah. All right, after that, then we have this inequality. Right. With this inequality, if I ask you to count the number of I that fall in this range, can you calculate it? Number of I's that fall into this range. Do the counting. Similar as we did for the number of leaves in the leaf range. Yeah. This calculation, the answer. Upper bound minus lower bound plus 1, right? Upper bound minus lower bound, then plus 1 back. So we have this, you can see similar expression, similar form. If you compare it with our number of leaves, that formula. So floor function of n over 2 minus floor function of n over 4, 2 squared. Yeah. Yeah, so this formula, yeah, pretty neat. Yeah, here. And this one, remember, in the previous slide, we simplify that 2-term expression to 1-term expression. Here, we can also do the similar thing, but when we do it, notice here it is an inequality. We cannot use equality. Not if you use the equal sign, that is false. Because for some of the n's, the inequality holds. The equality not hold. Yeah. So we should be careful. Yeah. Here, the inequality here. Yeah. Fortunately, later when we estimate the building costs of a heap, we only need to use this inequality. We don't need the equality. So inequality is good enough for us. Yeah. All right, so let's leave go to the next step. Now we can consider the general case, right? After we did height 0 case, height 1 case, can we observe some special rule for the general height h case? General height h, can we write that number of internal nodes with height h formula? Yeah, we generalize the previous result. Number of leaves, this expression. Height for 0. Number of nodes, yeah, we can, skip that internal. We know height 1 must be internal. So number of nodes with height 1, this formula. Yeah, the range, yeah, we write range first. Then the number in this expression. Okay, all right. Next, number of nodes with height h, the general case. First, the range. Can we use analogy? Analogy from the above formula to get this one, right? Yeah. Analogy, the upper bound floor function of n over 2 to the h, that power number. Yeah, 2 to the h. When h equals 1, that's the same as our height 1 formula, right? Yeah, yeah. So, and the lower bound also, when h equals 1, the same as the height 1 formula. Yeah. But we can change the h value so we can get all height h number formula. Yeah. Then count the number of nodes with height h, upper bound minus lower bound plus 1 back. So that's this formula. Okay. And remember inequality. There is an inequality. Yeah. I didn't write here. Yeah, let me go back a little bit. Yeah, but remember, we can write this ceiling function n over 2 to the h plus 1 floor function, right? Yeah. Because later when we do cost estimate, we need to use this formula. Okay? Yeah. So let us put it here on hold. We will move to our next part, B.2. So now we are ready for B.2. All right. All right, so B.2, yeah, we did a little bit. All right, yeah. So here you can see this one. Now we pick it up, right? That's the upper bound. Yeah, from our previous slide. We estimate the number of nodes with height h. This is upper bound. Yeah. Although we say upper bound, but the difference is very small. So there is a small difference. The difference is very small. So it is a very good upper bound. It is not a rough upper bound. It is a pretty accurate upper bound. Yeah. So we can use it with good confidence. Yeah. So let's continue our next development. Yeah. Then look at this. All right. Oh, yeah. I need to erase. Oh. Yeah, it's hard to erase. Yeah, I mean, that's the software problem. All right. That's a software problem. Yeah. So you can see, remember the annotation I wrote here before I stop my slideshow, I restart a new slideshow. But in our new slideshow, I cannot erase the annotation from the old slideshow. Yeah, that's the software problem. The software, cannot pick it up, cannot recognize the annotation from the previous slideshow. Yeah. Anyway, yeah. All right. Here, I hope you can see this big O of H each. What's the meaning of that? Yeah. Remember here, we try to estimate the cost. All right. try to estimate the cost. And we know here we consider a node with height h. So there should be some path from the current node, starting point here, and then reach the bottom level with height h. Okay, all right. Then the cost. What's the meaning of cost, right? When we apply the max heapify operation, we need to do swap operation. The worst case, all the way down to the bottom level, right? Worst case, all the way down to the bottom level. Yeah. Because sometimes we may not have the worst case. We stop somewhere in the middle. If somewhere in the middle, we notice that there is no violation, then we stop. Only when we detect there is a violation, then we continue the swap operation. If you recall the max heapify operation, we did in that way. But from current position, swapping down to the bottom, that's the worst case. Yeah, here we need to use the worst case, right? Yeah, here, worst case, that cost is big O of H, or big theta of H. If you want to write big theta of H, that's fine. Yeah, that's better, more accurate, better. Yeah, but for us, we mainly were interested in the upper bound. So we use big O, so that's fine. Yeah, yeah, that's fine. Yeah, that notation, small difference. Yeah, not a big deal here. Yeah. All right, so let's continue. Yeah. Next one. Yeah, I covered that. Yeah. Heights. Yeah. Heights from 1 to log. Yeah, so I can erase some of them. Yeah, I can erase the new annotation, but I cannot erase old annotation. So these old I cannot. Oh, yeah, new I can erase. Yeah, heights from 1 through floor function of log of n. Yeah, 0, the ground level, there is no cost, right? No building cost, because ground level we do nothing. Height 0, we do nothing. So we skip the height 0 case. So we start from height 1 case. All right. Now skip the leaves. Now let's look at the cost expression. This is the cost expression. Summation. Summation notation. I hope you know the summation notation. Big sigma summation notation. Yeah. And 2 parts. The first part, the number of nodes with height h, the first part. The second, the cost for each node. Cost for each node. All right, so, okay, yeah. So that's the expression. Okay, that's the expression. All right. Now let us try to estimate. Yeah, try to estimate. Yeah. Because the seeding function not easy to handle, so we want to remove that seeding function. If you remove, we need to make it larger by adding 1. Now, we know the function expression without seeding function, that is a little smaller than the seeding function expression. So, but if we add 1, it will be greater. So we can use this less than or equal sign, yeah, to do estimation. In this estimation, there are 2 terms. inside the parentheses. The first one is a fraction expression, second one is constant one. So we can split these two terms, we can split. We do summation separately for these two different terms. For the first term, this is the summation. For the second term, we have the summation. Okay, yeah. Let us estimate each one separately. Yeah. For the second one, that is much easier. So let us do it first, the second one. Yeah. For this one, yeah, big O, we can treat it as just some constant multiple of H. Yeah. We can treat it as, this term, because big O, we may not feel comfortable. How do we do calculation on big O, right? Yeah, but if we assume we just work on constant H multiple of H, constant C times H, then it's pretty easy, right? Yeah. So the big O, we just apply the formula, yeah. Floor function, integer, but we replace the floor function. Yeah, actually, yeah. Okay, yeah, still big O, yeah. So we can get this estimate. This estimate, big O of log n squared. Not n squared, it's a log n squared. Yeah. So let's put it here. Yeah. Later, after we find the expression for the first summation, then we will put them together. Okay, yeah. So our next task, estimate the main term. This one a little harder. Okay, this one a little harder, but not too much harder. Yeah. This time we need to consider this summation. Yeah. For this summation, yeah, let us simplify it, because in the summation, n never changes, and this n number never changes. Okay. From beginning to end, after we select n never changes. When we do summation, here, what I mean, when we do summation, that n never changes. Okay, yeah. If it never changes, we can treat it as constant, right? H changes, right? H in first term, second term, third term, all those H values are different. But n in the first term, second term, third term, in all the terms, H number keeps the same. That's the meaning. I say n never changes. If n never changes, we can treat it as a constant. If it is a constant, let us take it out, factor it out of the summation expression to simplify it, make it a little simpler. Other than that, because n is outside, when we consider the summation part, we do not need to look at that n part, right? Let us just focus on the summation part. How do we estimate that summation part? The summation part, we change the upper limit. Upper limit, that's the floor function of log of n. If we replace floor function of log n to infinity, we change that to infinity. That means we add more terms, right? Yeah. We add all the remaining terms through infinity. Definitely the summation expression becomes larger. Now, here you can see we are very generous. We enlarge the summation expression in a very generous way. Now, why we are so generous here? Because even we make the upper limit to infinity, we can still get a very nice estimate. And the computation will be much simpler. Here you can see if we change the upper limit from a finite number to infinity, the computation becomes easier, not harder. All right, that's interesting. Yeah. Let me show you the trick. Yeah. There is a little algebra trick that we can take advantage of. Take advantage of the property of infinity. Infinity has some nice property. Here we need to make use of that nice property of infinity. All right, let's do it in the next slide. Yeah. Next slide, we want to calculate the summation of this expression. Yeah. That is exactly equivalent expression of that summation one, but we write all the terms explicitly without sigma notation. Here we write the summation without sigma notation, term by term, term list, this notation. Because using this term list notation series, yeah, we call it series, yeah. In this series notation, yeah, we can apply special operation, apply the trick to find the answer in a smart way. Yeah, let me show you the smart way. Yeah. All right, right here, calculate the summation. Yeah. S. Oh, S. What's that? All right. A little different. Yeah. All right. A little different. Yeah. Sorry. Yeah. Why I say that? Yeah. I need to modify because S, based on our previous slide, it should be 1/2 plus that. All right. Then 2S, it should be 1 plus that expression. I need to modify it. I just found the mistake here. Yeah. S equals 1 plus that the remaining terms. 2S, 1 plus remaining terms. Yeah. All right. Now let us compare these two formulas. Compare the like terms. The like terms. So what's the like terms? Yeah. 1/2 to the h term. Yeah. H equals 1, 2, 3, and so on. The like terms. Let's compare the like terms. Look at the like terms in this diagonal way. Okay. In the first line, the numerator is 1. The second line, the numerator is 2. Next pair of like terms, the first one, the numerator is 2. Second one, numerator is 3. You can see the second line, the numerator is 1 more than the first term, and so on. That's true for all the diagonal pairs of like terms. How about that? The diagonal way to choose the like term pairs, we have that property. All right. Then we do subtraction. The bottom line subtract the upper line. S equals, now we have 1/2 plus 1/2 squared all the way 1/2 to the h to infinity. And we know this geometric series, its summation is 1. That's simple. Yeah. You know how to calculate it, right? We have a formula, right? This infinite geometric series, we have formula 1/1 minus 1/2. How about that? Not that. Okay. All right. The first term, 1/2. Yeah. The first term, 1/2 over 1 minus the common ratio. that is 1. Yeah, that's the formula. Okay, the first term over 1 minus the common ratio. Okay, the common ratio. Yeah. All right. The answer is 1. S equals 1. Yeah. So with this estimate, let's go back to building a heap. Now we can find the total estimate. Yeah. Because after we factor that, after we factor in that big summation thing, and this is estimate, it's 1. All right. Yeah. Although with some big O outside, 1, so that's big O of n. Big O of n. Then let us bring back the second summation. The second summation, log n squared, that is dominated by the first term. The first one dominates the second one. So we do not need to consider the second summation. Comparing with the first summation, it's too little. We can ignore. Now, the final conclusion, the total building cost, big O of n. Now we get a conclusion, the building cost, final, big O of n. Final conclusion. Okay? Yeah. So we complete this part. All right. Then the last topic, B.3, Heapsort and efficient analysis. We have less than 10 minutes, but this part is pretty easy. After we did preparation at this point, so far preparation, we're almost there. Yeah. The last step, almost there. We just do some simple work. We will be there. But the idea is quite interesting. The Heapsort idea is quite interesting. So let me describe the Heapsort idea. And the efficiency analysis, just trivial. Just, simple, a few lines. We can get it. Hopefully we complete B.3 today, so we do not need to come back to this topic in our next class. All right, so let's start the Heapsort. Idea of the Heapsort. Let me use the diagram to explain the idea. The key, let's make some key observation here in this diagram. All right. Let us consider, suppose here we have a max heap. Yeah. We build a heap. Suppose we have a max heap here. Yeah. After we spend this cost, the big O of n, yeah, that cost is acceptable, not too bad. So we are willing to spend this cost initially. All right. So big O of n, yeah. Max heap. Now, in this max heap, we know the largest element is at the root. This simple property is our starting point. When we start, we work on the root first. How do we manipulate this root element? The question, remember the goal of sorting. The goal of sorting. What's the goal of sorting? If I use a simple sentence, put all the elements in place, right? All the elements in place. That's the goal of sorting, right? The question, when we start from root, can we put the root in place? We want to put the root in place. That's the first thing we want to do. Yeah. The question, how to put it in place? What is the right position for the largest element in the array? Pretty obvious, right? Here, let me use this line segment to represent the final sorted array, the position. Yeah. At the beginning, we know the root takes the first location The first location here we mean index 1, not 0, okay? Not 0. We skip that 0 location. Yeah. Location 1. Yeah. And then, yeah, so here, that's the current location. Yeah. Then the final location of the root, it should be the end, the final location of this array n, right? Yeah. Location n. Yeah. That means we should move the root from the first location to the last location. That move, we know, swap operation, right? That move is a swap operation. Yeah. The last location corresponds to the heap binary tree, that is the red circled node. Yeah. So you can see we need to do this manipulation. We need to swap the first node and the last node. That's all we need to do. Yeah. So here, let's look at the operation. Swap A of 1 and A of n, the first step. All right. After the swap, you break the max heap structure, right? The max heap structure is violated by the swap operation, right? But we can fix it. We can fix it by max heapify operation. So after that, we need to recover the heap, the max heap structure. Yeah, here we mean the max heap. Okay, yeah. We need to recover the max heap structure by the max heapify operation. Apply the max heapify function, call max heapify function. All right. Now the procedure of heap sort. With that observation, now we can write the formal heap sort. We do iteration. At the beginning, we build a max heap of array A with the building cost big O of n. Yeah. So we take it. That's fine. Yeah. After that, we do iterations. I from n down to 2. Yeah. From n. Yeah. The root at the beginning, n nodes. Down to 2, not 1, because when we reach I equals 1, we do not need to do anything, right? Yeah. We just, put it right in place. It's already in place. So we don't need to do anything for I equals 1. So that's why we only need to do manipulation when I from n down to 2. Okay, yeah. First, we swap A of 1 and A of I. Yeah. I, the current location for the end of the subarray. Yeah. Because after this I location, all other location elements, all the elements in the locations after I are already in place. So we do not need to worry about that. All right, so swap A of 1 and A of I. After that, reduce the heap size by 1. Why reduce heap size by 1? Because one more element is in place. The reason, one more is in place. So that's why we should reduce the heap size by 1. The current heap only covers the elements that may not be in place. So reduce the heap size by 1. After that, we apply max heapify operation on the current array A, although we still use A, but we know it stores a subarray, okay? Subarray. Excluding those elements that are in place, subarray. What is this 1 starting point? Max heapify 1 means the root. 1 means the root. We always start from the root. Because after we fix the heap, the root 1 is the largest element in the current subarray. Yeah. All right. So we run this for loop, then we can sort it. The sorting cost, you can see when the heap has n elements, the cost is log of n. N minus 1, the cost is log of n minus 1. Why this much? Yeah, because the height, this corresponds to the height. That log corresponds to the height. So you're adding up, yeah, there are n minus 1 terms, right? N minus 1 terms. So that will be less than or equal to n times log n. N log n, all right? N log n. That is the acceptable efficiency expression for a sort, right? So this is acceptable. So the heap sort has the efficiency n log n. Think about that. So that's good enough for us. Okay, yeah. So we complete the heap sort topic. All right, so that's it. Yeah. So we finished part B. Yeah. Next time I will talk about hashing technique. Yeah. It's important. I may not go very deep, but it's important. Yeah. All right, so let's stop right here.